In this lecture, we're going to discuss a definition of absolute value of a real number and establish some properties of absolute value based on the axioms and theorems that we proved last time. So, first of all, the definition of absolute value of x, the absolute value of x is defined in the following way using the standard notation. Absolute value of x is defined piecewise. It is equal to x if x is greater or equal than 0, and it is equal to minus x if x is less than 0. Then another definition that follows from this one. So this definition works, of course, for any real x. So given any x, which is a real number, we can define the absolute value. Second definition, the distance between the two real numbers a and b is, I'm going to denote it by distance from a to b, and that, not surprisingly, is simply the absolute value of b minus a. Right, this is obvious, and I'm sure it makes a lot of sense. Okay, so with absolute value and distance defined in this way, let's talk about properties of the absolute value. And we're going to summarize them in the following theorem. So, theorem. I'm going to suppose that A, B, C, whatever many numbers I need in the statement of this theorem, that are all real numbers. So then the following items are going to be true. 1, absolute value of A is always greater or equal than 0. Number 2, absolute value of AB is equal to absolute value of A times absolute value of B. And number 3, absolute value of A plus B is less or equal than absolute value of A plus absolute value of B. This last property is something called triangle inequality, and I will explain it shortly. Okay, so then with this theorem in mind, let's try to prove all items here. So proof of the item number 1. What is the absolute value of A? It's, again, A if A is greater or equal than 0, and it's minus A if A is less than 0, right? So the first part of this is well already done, right? If A is greater or equal than 0, then absolute value of A is equal to A, so there is nothing to do in this case. And then in the second case, So when a is less than 0, then let's see, we had a theorem in which we established that if a is less or equal than b, then minus b is less or equal than minus a. That was, I believe, theorem 2 from last time, item number 1. And I think I called it 1. So from that item, then we have that 0 is going to be less, sorry, when a is less than 0, right? So then 0 is less than minus a, right? So then we got that minus a is positive. And so then in the second case, we're done as well. So once again, if a is greater than 0, absolute value of a is a, so a is greater or equal than 0. If a is less than 0, then we multiply inequality a less than 0 by minus 1, and we get minus a is greater than 0. So regardless in what situation you are, the value of absolute value of a is going to be positive. Okay, let's do number 2. We're taking absolute value of a times b. And what do we have here? We have that this is equal to a b if product AB is greater or equal than 0, and is equal to minus AB if product AB is less than 0, right? So that's what we know. And so in this case, it would be enough actually to consider different cases. So case, how many cases have we got? A can be positive and negative, B can be positive and negative. So any combination of positive or negative A and positive or negative B would do. So we have 4 different possibilities. So possibility number 1, A is greater or equal than 0, B is greater or equal than 0, right? Then we're in a situation, again, described in a theorem about ordering that we proved last time. And actually, let me label that theorem the way it appears in the book. So this is 1 in theorem 3.2. So if we look again at the theorem 3.2, item number 3 tells us that if A is greater than 0 and B is greater than 0, then A times B must be greater or equal than 0. And so therefore, if I take absolute value of AB, so then absolute value of AB is equal to A times B. Absolute value of A is equal to A, right, because A is positive. And absolute value of B is equal to B because B is positive. But then, of course, I can conclude from this that absolute value of AB is AB, where A is absolute value of A, and B is absolute value of B. So I'm done in this case. Item number 2, let's say A is less or equal than 0, B is greater or equal than 0. So what should we expect in this case? So in this case, if A is less or equal than 0 and B is greater or equal than 0, then we know that absolute value of A is equal to minus A, right? Because A is negative. And absolute value of B is B because B is positive. Okay, so what do we know about AB? So if we consider AB, so A is negative, B is positive. Then if we go to the axioms of ordering, in axioms of ordering, we know that if certain inequality is true and I multiply the inequality by a positive number, then the sign of the inequality stays the same. So because A is less or equal than 0, then by multiplying both sides of this inequality by B, which is positive, I can use the property O5 to conclude that AB is going to be less or equal than 0 times B. And then we use theorem 3.1, item number 2, which allowed us to conclude, so this is item 2, that 0 times any number is 0. So AB is less or equal than 0. And if AB is less or equal than 0, then by properties of absolute value of AB is equal to minus AB. All right. And then in addition to that, again from the theorem 3.1, theorem 3.1, number 3 now, theorem 3.1, item number 3. What do we know? That minus of AB is the same thing as minus A times B. So this implies that absolute value of AB is equal to minus A times B. And now we utilize what we already said about absolute value of A and absolute value of B. Minus A is the same thing as absolute value of A, and B is the same thing as absolute value of B. So that means that we're done, right? Because again, we established that absolute value of AB is absolute value of A times absolute value of B. 3, A is greater or equal than 0, B is less than 0, or less or equal than 0, doesn't matter. The same approach as in number 2, right? Because role of A and B is reversed, but the idea is exactly the same. And then item number 4, last possibility. A is less than 0, B is less than 0. So what are we going to do in this case? Again, by definition of absolute value. In this case, absolute value of A is the same thing as minus A, and absolute value of B is minus B. Okay, fine. So then what can we say about AB? So I'm going to consider AB. So the question is AB positive or is AB negative? So one thing then we can try, let me see what sort of properties we have. So if I look at inequality A less than 0, right, that is given to me. Let's consider the theorem 3.2, item number 2. There we discovered that if we multiply a number, an inequality by a negative number, then the sign of the inequality should switch to the opposite. So if A is less than 0 and B is a negative number, if I multiply A less than 0 by B, then what I'm going to get is that B times 0 times B is going to be less than A times B. Once again, from theorem 3.1, from a theorem 3.1, we know that a number times 0 is equal to 0. That's theorem 3.1, item number 2. We get that 0 is less than AB. So AB is positive. And so therefore, if I take absolute value of AB, then this should be the same thing as AB, right? Because AB is positive. And finally, if we look at theorem 3.1, item number 4, this tells us that if we are multiplying minus A by minus B, that is the same thing as AB. So therefore, absolute value of AB is actually the same thing as minus A times minus B, right? Because AB is the same as minus A times minus B. And then finally, we use the definition of absolute value of AB that we have here. Minus A is absolute value of A, and minus B is absolute value of B. So absolute value of A times absolute value of B, and we're done here. So that means that we have a pretty lengthy computation, but we covered all 4 cases. And so then we're done here as well. All right, let me just label the end of the proof in item number 1, end of the proof in item number 2. And so now we look at the triangle inequality, item number 3. So in this case, what you could do, you could also consider cases just like we did in a case when I took absolute value of the product. But rather than doing cases explicitly, I'm going to utilize some additional inequalities which will make the procedure slightly faster. So note that, and actually I'll ask you to prove this for yourselves, that if I take A and I compare it with absolute value of A, then for sure I know that absolute value of A must be less or equal, absolute value of A must be greater or equal than A. So again, I would ask you to verify this. And minus A, and A is bigger than minus absolute value of A. So verify this. And if this is true for A, then exactly the same thing is true for B, that if I take minus absolute value of B, that's less or equal than B, which in turn is less or equal than absolute value of B. Okay, so with that, let's now try the following. So I'm going to take the first inequality. I'm going to rewrite it minus absolute value of A, less or equal than A, less or equal than absolute value of A. I want to add, oops, B to all sides of this inequality. And this will give me minus absolute value of A plus B, less or equal than A plus B, less or equal than absolute value of A plus B, right? So that's one thing that we have. But then we know a couple of other things. So also, if I take the half of inequality, B less or equal than absolute value of B, and then I will add absolute value of A to both sides, which I can do by, I'm not listing this as listed now, but I will be able to do it by using the property, I believe, O3, that I can add the same number to both sides of the inequality. Then what this will give me is that B plus absolute value of A must be less or equal than absolute value of A. Actually, let's write this in a different order. Absolute value of A plus B should be less or equal than absolute value of A plus absolute value of B. So I'm using O3, and I'm also using the commutativity of addition that I can interchange two items in the addition. So we have this. And also the second half of this inequality about B minus absolute value of B is less or equal than B. And so I should be able to add, I should be able to, let me see if that's what I actually want. Yes, I should be able to add minus absolute value of A to both sides. And what this will give me minus absolute value of A minus absolute value of B is less or equal than minus absolute value of A plus B. Right, so once again, I'm doing the same thing. I'm using the property O3 and commutativity of addition. So then we can try to combine different inequalities here. So I'm going to rewrite this guy. But now I know something else. I know that absolute value of A plus B is less or equal than absolute value of A plus absolute value of B. So I can stick this here. And from the second inequality, I know that minus absolute value of A minus B is greater or equal than minus absolute value of A minus absolute value of B. So I can remove the intermediate inequalities, and I have minus and I'll actually factor out the minus sign in here to get minus absolute value of A plus absolute value of B less or equal than A plus B, less or equal in turn than absolute value of A plus absolute value of B. All right. Okay, so what sort of things then can I conclude from this? Well, what is the absolute value of A plus B? Absolute value of A plus B is one of two things. It's either A plus B if A plus B is greater or equal than 0, or it is minus A plus B if A plus B is less than 0, right? That's just the definition of the absolute value. Well, but then from the first, or rather the second inequality here, what do I see? I see that always, no matter what, A plus B is less or equal than absolute value of A plus absolute value of B. So I can conclude that in this case, I'm less than absolute value of A plus absolute value of B. Okay, what about the second case, minus A plus B? Well, so we'll look at the second inequality, or first inequality here. It says that minus absolute value of A plus absolute value of B is less than A plus B, but I can as well multiply both sides of this inequality by minus 1. So, because, oops, and I will write a conclusion in a second. So, because minus A plus B, sorry, minus A plus B absolute values is less or equal A plus B, this means that minus A plus B is less or equal than absolute value of A plus absolute value of B, right? This is again the property theorem 3.2, I think, 2. Multiply both sides of, or 3.1 times, yeah, 3.2 times 2. Multiplying both sides of inequality by a negative number is going to flip this inequality. Well, but then that means that minus A plus B actually is also less or equal than absolute value of A plus absolute value of B. So in this case, I'm still less or equal than absolute value of A plus absolute value of B. So in all cases, absolute value of A plus B is less or equal than sum of the absolute values. And so then again, we're done. We proved the triangle inequality. All right. So with these established, let me explain why the triangle inequality is called triangle inequality. So let's look at the distance between two numbers, A and C. What is the distance between A and C? That is, according to our definition, absolute value of C minus A, right? Well, so if it is equal to absolute value of C minus A, then given some third number B, what I can do is subtract B, add B, keep A where it was, right? So that obviously doesn't change anything. But then my inequality that absolute value of A plus B is less or equal than absolute value of A plus absolute value of B implies that this must be less or equal than absolute value of C minus B plus absolute value of B minus A. And who is absolute value of C minus B? That is the distance between B and C. And absolute value of B minus A is the distance between A and B. So this says that, so therefore, the conclusion from this is that the distance from A to C must be less or equal than the sum of distances from A to B and the distance from B to C. So if I go straight from A to C, somehow I'll always get from A to C not slower than by going from A to B first and then from B to C. In this case, all numbers are just on a number line, but exactly the same situation will happen in 2D, for example, on a plane. If I have a triangle, and let me draw a better triangle than this. If I have a triangle on a plane, and I label the vertices of this triangle as A, B, C, then clearly distance from A to C is going to be less than the distance from A to B plus the distance from B to C. So that's why this is called a triangle inequality. And apparently, as you can see, it is also true in 1D. All right, so in the next lecture, then we're going to talk about properties other than these axioms that we and theorems that follow from them, axioms of an ordered field, which we said will work in the same way in both the set of rational numbers and real numbers. And we're looking for properties that are actually going to be distinct between these two sets. And then in the next lecture, we're going to talk about something called the completeness axiom, which will distinguish between Q and R.